All right, I was like, just before I was like, I'm sure I'm forgetting something. Is just something that I forgot to do, and I forgot to embed the event into the live video into the event page. So for all the folks who are waiting to watch that on the Google Plus event page, I deeply apologize. Feel free to join us whenever you want. So hey everyone, my name's Fraser Cain. I'm the publisher of Universe Today, and this is your weekly space hangout for Friday, June 6th, 2014. This week, we'll be talking about Mega Earth. Is NASA really going to be on track to go to Mars? An update on Cosmos. Evidence of the impact that formed the Moon. A strange hybrid star may be found. Magnetic field lines near black holes stronger than expected. And the Hubble, what I'm calling the Hubble Ultra Deep Field, but I believe it's just the Hubble Deep Field, Ultra Deep Field in ultraviolet. I guess it is the ultra deep field. Joining me this week, we've got Dr. Brian Koberlien. Hey, Brian.
Hi. How are you?
Good. We've got Dr. Matthew Francis.
Who is sick, so he may not be coherent.
Crazy Dr. Matthew Francis. And working on being Dr. Morgan Rehnberg. Hey, Morgan.
Fraser.
All right, well, let's get cracking. Now, before we do, actually, just want to remind you, you can talk to us, you can coordinate with us, and the way you do that is with the Q&A app, which is located conveniently in the middle of your YouTube viewing experience. So click the link, it'll take you to this weird interface where you can see the video and post a bunch of comments. And just to show that this works and to give you all valuable benefit, I'm going to say hi to Rich Hayward, Patrick Calhoun, OXYZABCX0, Jim Meeker, Nancy Graziano, Bert Wolters, Marian Baltazan, and Will-Eyed Oney. So, hey everyone, thanks for joining us, and let's get cracking. Let's start. What do I like? Well, let's start with Morgan. You put a story up here about whether NASA is on track to go to Mars, and this is a shocking surprise to me. What's going on?
Yeah, so released earlier this week was a report by the National Research Council. This is a branch of the U.S. National Academies, and they spent 18 months studying and reviewing NASA's manned spaceflight program. This was congressionally mandated, and they wanted to look and see, is NASA, do they have the right goals? Are they on the right track to meet those goals? And kind of across the board, the answer is no. This was a very in-depth report. They went all the way back to kind of asking the question, why do we send people into space? And is it worth sending people into space? And the answer that they came up with was, if you're only looking at the technical aspects of the things we get back from the space program, the technologies developed, the people educated, etc., then the money we spend on space exploration is not worth it. But if you lump in sort of the inspirational aspects of space exploration, getting the next generation of scientists and engineers and educators excited about science, earning the United States goodwill globally, then you can justify the cost of the program. But because the inspirational aspects are so important to justifying the cost of the space program, and we spend about $18 billion a year exploring space through NASA, then it should be NASA's goal basically to aim as high as possible, to do the things that will inspire people. And so the National Research Council interpreted that as going to Mars and putting people on the surface of Mars. And from that starting point, they looked at what NASA is doing in space today with the question, is this helping us get to Mars? And in some things they're doing, the answer is yes. Like learning to live in space on the International Space Station will help us understand what we need to do to take care of astronauts over the course of that 6 to 8 month journey to Mars. But other things that we're either doing or planning to do maybe don't align so well with those goals. An example they threw out was the planned asteroid capture mission that is sort of President Obama's headline goal for NASA these days, is to send out a robot, capture a small asteroid, put it in orbit about the moon, and then use the brand new Orion capsule and the Space Launch System to send astronauts up to that asteroid to do science on it. And this report suggests that a lot of the technology that will develop to do that mission isn't technology we actually need to go to Mars. And if our goal is go to Mars, go to Mars as quickly and efficiently as possible, then we shouldn't get sidetracked with some of these other projects, especially when something like studying an asteroid can be done pretty well robotically. And in fact, next 2016, the OSIRIS-REx mission will launch to go to an asteroid, scoop up a sample, and bring it back to Earth. They also took a look at whether NASA had the budget necessary to go to Mars. And probably unsurprisingly to everyone, the answer to that is no. It would cost hundreds of billions of dollars to develop a Mars landing program. It cost about $150 billion to build the space station. It cost about the same amount of money to put people on the moon. And so to get to Mars is going to be a challenge beyond either of those. And they estimate that NASA's budget would need to be increased by about 5% every year for, the duration of the Mars program in order to provide enough funding to get people there safely and efficiently. And, it's tough to see that as a politically viable goal right now. I mean, Casey comes on once in a while and cheers when we get an extra $100 million. We're talking about adding, on the order of $1 billion a year to the space program every year from now until we land on Mars in 15 or 20 years. And that's going to be a tough sell today. It's going to be a tough sell in the future.
Well, I've already figured this out, and perhaps people who've been watching the show for a little while know that. But in my mind, when I put on my I'm the NASA administrator hat, which I guess I can't because I'm Canadian, but let's say that I did. It really needs to be the purpose of manned space exploration, of human space exploration, is to learn how to have humans live in space, beginning in the end. I really think that all those other things about doing science on asteroids and science on the moon and all that kind of stuff, you can justifiably have robots, cleverer and cleverer robots, do a lot of science, scientific observatories. And the problem is that as you try to have these make-work projects for your astronauts, it's taking away from these science budgets. So, you want this ladder of tasks that you want these astronauts to be doing. Now let's learn how to survive in space for 1 year. Now let's learn how to survive in space in low gravity. Now let's use this kind of mission, etc. And really, at every point, it's literally just let's test out our space hardware and make sure that we can do this. And do the next step, and that's what NASA was doing back in the heyday, back with the Gemini. Remember, it was like, now we're docking, now we're doing a orbital docking, now we're trying to, now we're going to go to the moon, now we're going to do a flyby of the moon, and each time it was literally just, can we accomplish this task and keep our meat humans alive, and because we need to become a spacefaring race, and the only way to become a spacefaring race is to learn all the steps to become a spacefaring race. So I think that any goal that just keeps that list of tasks, goals up there, and not try and explain it in any other way except that we're trying to push our boundaries out further and further and further, makes sense. And you just can't justify it over the long term because robots are so great. And when the robot apocalypse happens, I hope they kill me last.
Yeah, I mean, the bottom line here is that if we're going to do it, we have to say we're doing it, and we're going to have to get on with doing it. Because if we're not going to do that, we're just going to spend a lot of time kind of flitting from idea to idea. We're wasting a lot of time, and we're wasting a lot of money. You could send about 50 Curiosity-sized rovers out to the planet, to the solar system, for the cost that it would take to put people on the moon, or to put people on Mars. And you get a lot of science done by going to Europa and Enceladus and Titan and Venus and Mars and Mercury with these rovers. And so if all we want to do is kind of run around trying to do things, then that's a better way to go than to spend money on the manned space program. But if we want to say, yes, we want to be a spacefaring race, we want to be inspired by the things that we can do by pushing our boundaries, then we have to go out and push those boundaries. And going to an asteroid and orbiting it for a few days and picking up some rocks and coming home isn't really pushing those boundaries. It's going to Mars. It's going back to the moon in a permanent way. That will push our human space. If we're not going to do that, then it's hard to justify really doing much at all.
Yeah, and there's a bunch of things that we need to work on, like generating artificial gravity in space. That hasn't been thought through yet, right? Like, with rotating spacecraft, Matthew, not with Star Trek
Put all
space
the Higgs
magic.
bosons in one place,
Yeah.
right?
Yeah,
all the
yeah,
Higgs
just say no. I'm just saying, you either it is a difficult problem to solve artificial gravity simply because you can sit down and do the introductory physics level problem. You either have to have a very big spaceship or you have everybody barfing.
You have a long cable and a counterweight, and then you just rotate the two around a common center of.
Yeah, I know. That's obviously.
Then turning and adjusting tracks.
The only thing close to practical design, but
Right, but all I'm saying is that
Yeah.
is a long duration spaceflight is going to depend on some kind of micro artificial gravity, not the microgravity, and so that hardware needs to get launched into space, and human beings need to sit inside of it, and it needs to be tested, and that's the kinds of technological adaptations, keeping plants alive, recycling, materials for longer and longer periods, trying to create these closed environments, closed ecosystems, dealing with radiation. Like, all these things need to be figured out, and there's plenty of science and work to be done without having to muddy it with additional justifications. And I think that's crazy, and I would never do it. So, but I am not in charge. So what are you gonna do? Enjoy your never going to Mars. I'll take you there. I will take you to Mars. All right, let's move on. I think we're now going to talk about a really wacky hybrid star, Brian Koberlien.
Okay. It's called a Thorne-Zytkow object, and it was originally proposed in the 70s by Kip Thorne and Ann Zytkow, which is why it's named that. The basic idea is, what would happen if a neutron star and a red giant were to collide and merge? And there's some various scenarios for this where you could just have a random encounter and they collide and then coalesce with the neutron star in the center of the red dwarf star. Other ones have been, there's a close binary of a neutron star and another star, and then when it goes to a red giant, it causes drag on the neutron star and engulfs it. But the basic idea is that once this occurs, you could have a neutron star in the center of a red dwarf star. And this was proposed originally for some kinds of variable stars that behave kind of strangely. It does a couple of things. Because a neutron star is very tiny, it's only about 10 to 15 kilometers wide, it would be right at the central area of the star. They're also very hot and very dense. And so one of the things that it could do is rekindle fusion within a red giant star. Basically, a red giant is at the end of its life. It doesn't have a mass to fuse higher elements. And so, it's basically just going to be on its edge of dying. If you have a neutron star in the center, then all of a sudden you have enough temperature and gravitational pressure to induce higher order fusion. So you can get fusion of more elements than you could just by the red dwarf star alone. So this is one of these crazy ideas that shows up in astronomy every now and then. It's kind of neat, and it kind of gets put off to the side because the likelihood of it is extremely tiny. The chance of a neutron star and a red dwarf merging seem extraordinarily unlikely. Okay, so flash forward to just recently. There was a survey that was being done of red dwarf stars, and of these red dwarf stars that they were looking at, they found one looks like a red dwarf star, but when you look at its spectra, it's a little odd because you can look at the spectra and see what type of elements are in its atmosphere. In this case, they found an abundance of lithium and rubidium, which those types of elements in abundance within the atmosphere of a red dwarf are extraordinarily unusual. You wouldn't see this type of spectra. It's, however, the type of spectra that you would see with this Thorne-Zytkow object. So basically, they found this red dwarf that has an unusual spectra. It matches some of the predictions of a Thorne-Zytkow object, and therefore might, and I say might, be such an object.
So sorry, was it a red giant or a red dwarf?
Sorry, red giant.
Red giant. Okay, so not a red dwarf star. It's a
red giant. Yeah.
And so, I mean, the red giant is a temporary phase of a star's life. It's not gonna. So you've got to have this sort of I guess with your pre-binary object, you would have had to have a star that was massive enough to become a neutron star that also happens to be close enough to the red giant, to I guess to whatever the companion was,
Right.
during the phase that it's going to become. So it's like the odds are getting lower and lower and lower.
Yeah, I mean, one of the problems is the neutron stars are generally formed in things like supernovas. And so supernovas would tend to obliterate any star that was close enough to be able to capture it later when it becomes a red giant.
Would it really, like, completely, I guess, depending on how close it was?
That's the thing. It might not necessarily completely obliterate it, but the thing is you have this extremely large and violent explosion in close proximity to another star. And so, the chances of these types of things happening and then merging in the right way would be extraordinarily rare. Like I said, when it was originally proposed, it was like, here's an idea for explaining some of these unusual variable stars that we see. And it was an interesting idea, but it wasn't necessarily taken as a viable idea. But now with these new spectra, maybe you have it. They would still be extraordinarily rare, but it might be possible.
No, I mean, I guess it depends on the mass of the red giant that it's moved into, because in many cases, a red giant is still just going to be a normal stellar mass star like our own sun, right? That can turn into, our sun can turn into a red giant. So, but if you had like a red supergiant, then you may very well get, I don't know, I mean, is it going to turn into a black hole sooner because it's going to be gobbling it up from inside and have a supernova detonate from within, like a second supernova for the neutron star? It's also weird.
Right. Well, and part of the things too is that it would depend critically on the size of the star that it merges with. I mean, keep in mind the theory was outlaid in the 70s. So this is really before any type of advanced computational study. And because it was kind of an interesting idea but not seen as very probable, there hasn't been a whole lot of modern work done on it, on the theory side of it. So there needs to be more theory work done on it, and that may be inspired by this new discovery. But a lot of it still is pretty dated from the 70s and 80s.
Right. That's really cool.
We should point out, though, that there are X-ray binaries that consist of ordinary stars and neutron stars. So it's not so far-fetched that an ordinary star could survive. I guess you could conceive of, I don't know how much that would work, but you could conceive of a binary system where you have the formation of the neutron star, evolution of the binary, the ordinary star companion enters the red giant phase, and then somehow, don't know how, the neutron star drops into it. And that may be the key, is how does the neutron star drop into it without catastrophe happening?
Right.
And it's one thing to propose that this could exist, but how do you make it? That's the question I don't know the answer to, and maybe somebody else who knows more about stars could answer it. But
so in other words, if it was a catastrophic outcome, these things would then detonate or fall apart or whatever, or they get spun out, and then you just wouldn't see any evidence, because all you'd be left with is a regular neutron star, and you wouldn't see the carnage of what it had done to its I guess its pair star.
Yeah.
It's one of those ideas where you can come up with a scenario, but you can immediately come up with a lot of contradictions to that scenario. And say, but, and without any physical observational evidence to support that this strongly points in that direction, you kind of go, oh, that's interesting, but I'm not doing my PhD on it.
All right. Well, let's move on. So now let's talk about Mega Earth.
Okay, well, this is actually a planet that was discovered 10 years ago, I think. It's been around a while. It's Kepler 10c. So that's the 10th Kepler confirmed exoplanet discovery by so that puts it back a few years. But those who have been keeping track at home know that the Kepler Observatory discovers exoplanets via the transit method. So imagine my head is the star. Planet comes around and momentarily blocks a little bit of light.
Oh, there you are.
And so that's a really good way to measure the sizes of things. But it doesn't tell you anything about the mass. So to do mass, what you have to do is you have to measure the. There's several ways to do it. Well, 2 ways to do it that I can think of right off the top of my head. But you have to measure the wobble of the star as the planet orbits. So that really is heavily biased towards planets that are both massive and very close to their host star. In this case, the planet there's actually even a planet closer to the star, but this one orbits about once every 45 days. So it's pretty close in. And by measuring the wobble, they found that it is about 17 times the mass of Earth, which is about the mass of Neptune. But it is only a few times those 2 things, and it comes out to be about 7 times the density of water. Okay, Earth is about 5.5 times the density of. Is that right? 5.5 times.
Yeah,
what
5.3.
Okay, so it is much more dense than Earth. So you're imagining something that's, not that much huger than Earth in size, but much more massive and much denser. So that says it must be rocky in composition, but nothing like we've ever seen before. I mean, we're talking very compressed rock here. And it does not seem to have, not consistent with a dense hydrogen compound atmosphere like you have for Neptune and the other giant planets, the giant planets we know of in our solar system. So that makes this a very weird object, but also it doesn't seem to be consistent with what we know about planet formation scenarios. And that's where things get tricky, of course, because once something gets above a certain size, you expect it to start gathering hydrogen compounds and making a thick atmosphere. That's puzzling, okay? So it is one of those head-scratcher objects. So it'll be interesting to see if we can find other objects of this type, because the other thing that's interesting is that the star that it's orbiting, Kepler 10a is the designation, that's a fairly old star. So that means that not only is this rocky planet too big, it's too old. Nobody really expected to see a rocky planet that would form that early in the universe's history. So there's several mysteries we have to clear up here before we can figure out what this thing is. So I'll be interested in following this story because obviously there's a lot more we have to learn about it.
So, oh, what a surprise, our understanding of planetary formation is incorrect.
Again.
Yeah.
So
I mean, the hot Jupiters alone was a total surprise and shock, right? That you'd have these hot Jupiters that close to their parent star. Surprise.
And again, we may be seeing some migration here because that's the way we understand how a lot of weird planetary systems seem to have formed. The planet formed elsewhere and then migrated. Is that going to be the case for this? I don't know. That might explain why it got that big, but it doesn't necessarily explain why it doesn't have a big, thick atmosphere.
But we sure wouldn't want to live there, right?
No.
So.
Not in the habitable zone. Really close to its parent star.
Yeah, definitely not habitable.
A lot of mass.
Even if it were, the gravitational field would be strong.
Yeah, the gravitational field is what, 3 times that of Earth, roughly, at the surface? Yeah, so.
You wouldn't want that.
Yeah.
No, thank you. Well, that's really cool. All right, well, let's move on. So, Morgan, you watched Cosmos.
I did watch Cosmos. The next to last Cosmos, in fact.
The penultimate Cosmos?
An ultimate indeed. And it may have been penultimate, but this was probably going to be the ultimate episode of Cosmos in the sense that they really knocked this one out of the park. This was the third time, actually, that they had circled around to take a shot at climate change. And this time they went straight for it. And rather than kind of talking about sort of some of the philosophical, justifications for why we should care about climate change, they basically just deconstructed one by one all of the arguments that people make against, human-induced climate change, and showed, what are the consequences both today, tomorrow, and far into the future of climate change if we leave it unchecked. And really, I've spoken to several people who are big in climate change advocacy, and it's pretty well agreed that this is one of the most concise explanations and arguments for human change, climate change that we've really seen.
Is the irony overwhelming as the evidence? The fact that this ran on the Fox network?
Well, as I like to remind people, the Fox entertainment network is owned or is operated differently than the Fox News network. And in fact, that's an important distinction in all broadcasting. And so the people working on one really aren't the people working on the other, but I'm sure that they chagrin each other once in a while.
Yeah, I mean, just like to have that level of in-your-face climate change explanation when a whole other arm of the organization is doing everything it can to undermine the scientific evidence for climate change is
yeah, they didn't pull any punches, that's for sure.
Yeah, so that's amazing. No, I haven't seen it. Have you guys seen this week's one?
I haven't this week's.
I did.
And do you concur?
Yeah, I thought this was actually one of the better episodes, I thought. It was, I would say it was probably one of the better constructed episodes in terms of walking you through the process of how science is done. It was very systematic. I wish almost they would do that every episode because, one of my big things is how does science work, and this was the episode. And I know why they did it, because, of course, climate change is still considered controversial by far, far, far too many people. And so by being very systematic about it, you undermine each one of those arguments. You have to be able to, stick your head in the sand multiple times, or stick your head other places multiple times to really to reject all of those pieces of evidence. And so I thought it was very, very well done myself. I don't know how somebody who you would take it who was on the fence on the issue. Obviously, people who a priori reject climate change as being an ideological issue would not be convinced, but they're probably not watching Cosmos anyway. But I thought it was very well done.
It's interesting to me, and I haven't seen this episode, and I apologize. So but I mean, so far, I've watched the other 11, and that the choices they've been making are quite brave and very artistic, and they've been stepping away from what you would expect. Like if you told me what was going to be, Cosmos, it's Neil deGrasse Tyson, it's computer graphics, he's zooming around the universe, I would have constructed a series of episodes like, let's look at black holes, now let's look at stars, let's look at planets, and let's do the search for life, and those elements are in there, but it is not the show that I think anyone really expected, and I think that the artistic choices that they've made throughout the series, and especially with this kind of thing, that it is more, there's more art going on than I think, than it being a sort of technical job of showing the wonder of the universe. And I think it's great that it really made some connections back to the kinds of stuff that Carl Sagan wanted to talk about, and the kinds of things that he wanted to think about. Like it feels like his spirit is truly infused in this series, and good on everyone for doing that. I think it may be tough for them to get their second season while the universe has been cranking out season after season, or Morgan Freeman's Through the Wormhole, right, which has just gotten weirder and weirder season by season. But good on them for taking a lot of risks, and I think they really should be commended.
And if I can make one more point, the thing that, I recently rewatched the original Carl Sagan Cosmos, and the thing that struck me was how many episodes express the Cold War fear of nuclear annihilation. And really, climate change takes the place of that. I mean, you have the whole, we're going to destroy everything we love about our planet with nuclear annihilation. Climate change is a lot more inevitable than nuclear annihilation. The element of choice of, has a different.
Oh, you cut off.
Did I? Okay.
Yeah, your terrible internet.
My terrible internet.
So I totally agree with whatever I didn't hear.
Okay.
All right, well, let's move on then. Talk about magnetic field lines near black holes stronger than expected.
This was an interesting article that looked at jets coming off of what are referred to as radio galaxies, but radio galaxies are driven by black holes. And so they looked at the jets coming off of a black hole. So you have the black hole with an accretion disk around it, and then the jets come out in the regions of the poles. And from that, they could determine what is the strength of the magnetic field near the jets. And then they compared that with the brightness of the accretion disks around the black holes, from which you can get an idea of what the size of the black hole is and things like this. By comparing these two, they could then determine what the magnetic fields were in the region of the black hole itself. So in that very close region near the black hole. What they found was that the strength of the magnetic fields were much stronger than we supposed. So if you imagine a magnetic resonance imager, an MRI, if you think of the strength of the magnetic field within the center of an MRI when it's on, that's the strength of the magnetic field near these black holes. And this was consistent over a full, I think, 9 orders of magnitude. So a full range of sizes for black holes. So it's not just specific black holes, there's a full range. With a gravitational field, with a magnetic field that strong, that changes the way we approach the behavior of material around a black hole. Because usually we've looked at the material around a black hole, things like the accretion disk and stuff like that, are driven predominantly by gravity. And then the magnetic fields interact with that material and add kind of a secondary effect. And one of the things that they found is that the magnetic fields near a black hole are strong enough that they can affect the rate at which black holes absorb material. So what they call the infalling of material is inhibited by the strength of the magnetic field. So this is if this holds up, this is kind of a radical change in the way we view black hole evolution, because typically we would say that the amount that they accrete is really determined by their size and the amount of material. And what this is showing is that the magnetic fields are so much stronger, they actually play an equal role in the dynamics of black holes.
So that's sort of a countering force, that you've got this inflow of material coming into the black hole, and then you've got this magnetic field. But, I mean, the magnetic field is going to decrease with space as well. So aren't you going to get sort of material piling up in this magnetic field, or is it actually getting channeled and focused out in these jets?
Well, the magnetic field is still there within the material around it, so you still have this magnetic field. But the magnetic field will do things like distorting the accretion disk. So if you think of the accretion disk, you have the black hole in the center, and then you have this kind of disk around it of material. One of the things the stronger magnetic fields does is it squashes that disk. It makes it more pancake-shaped rather than being more open. So this changes things like the pressure and temperature of materials within the accretion disks themselves, because now you're squeezing them because of the magnetic fields. We're going to have to go back and look at new computer models because of this. So if we find that magnetic fields really are this strong, all the computer models get revised, because now we have to take into account the more strongly interacting magnetic fields with things like the accretion disk.
So if I fall into a black hole and I get spaghettified, but am I also maybe getting, I don't know, magnetized? Will my hair stick up as well? If I had any?
Well, the magnetic field would interact with you. Yeah, I mean,
Yeah.
depending on the size of the magnetic of the black hole, you could get spaghettified either outside the black hole or not until you cross the event horizon.
Would it, make your feelings hurt?
It would not be pleasant. I mean, falling into a black hole is a lose-lose situation, really.
Yeah. But well, that's interesting. All right, so I think you've got one more story as well. Actually, Morgan. The
Actually,
evidence.
can I break in for just a second?
Just in.
Can I advertise a class on black holes that's coming up in just a week and a half's time? If you want to learn about black holes, my other hat I wear besides science writer is director of Cosmo Academy, part of Cosmo Quest, partner organization with Universe Today. So please sign up. And now I'll turn things back over to Morgan.
But you're going to be instructing it, right? So you still got a few slots left to fill?
Yes. We've got several slots, and if enough of you sign up, we'll offer even more. So don't feel you're going to run out of options here.
Okay. All right. Cool. Well, let me know if I need to do the full pitch on how exciting and how great this is. But then,
We'll include
why
the link
go
in
to
the
university? Why attend university when you can take a deep dive into the topics that interest you? Is what I'm saying. And at a reasonable price, you can learn everything you ever wanted to know about black holes without having to have any pesky bachelor's degree in science or any of that. Matthew,
Everything you want to know about black holes, but we're afraid to ask.
We're afraid to ask, which is literally everything. All right, Morgan, we found the impact.
Maybe. So let's take a step back here. Our moon is strange. If you look at other planets in the solar system, the planets themselves tend to be about 100,000 times larger than the moons that go around them. So if you take up all the moons of Jupiter, for example, and you add them together, you get about Jupiter being about 100,000 times heavier. If you take all the moons of Saturn, you add them up, Saturn's about 100,000 times heavier than that. But the Earth is not even 100 times heavier than our moon. It's only about 81 times heavier. And, for a long time now, for decades, that's puzzled astronomers. And so they started asking, well, maybe the Earth's moon formed differently than other moons. We think moons, for example, around Jupiter, probably formed at the beginning of the solar system out of the same disk of gas and dust that's formed the Sun, that formed the Earth, and that formed Jupiter. And they just happened to form close enough to Jupiter that rather than becoming planets like Mercury, they fell into orbit around Jupiter instead of the Sun. That probably wouldn't work for our moon, though, because it's far too large. The Earth would have already taken up too much material in the area around the moon for the moon to have formed big enough. So we started thinking about what are other ways that something like the moon could have formed. And in planetary science, if you're not sure how something works, there's only one answer, and that's that something hit something else. And in this case, we said, well, what if way back at the beginning of the solar system, a body about the size of Mars smacked into the Earth? And way back then, there would have been more than the 8 planets that we see today. There would have been lots of Mars-sized bodies just kind of cruising around the solar system. And as time goes on, they either hit things or were thrown out of the solar system by interactions with planets like Jupiter. But before that happened, maybe one of them smacked into the Earth. And this would have caused an impact that almost destroyed the Earth. But instead, it just blasted a lot of material off of the Earth, and it would have formed this big ring around the Earth. Very quickly, then, that ring would have coalesced together to form the moon that we see today. And so that's kind of our best guess today about how the moon formed in relation to the Earth. So now we fast forward to the 1960s, and the Apollo astronauts land on the moon. They pick up moon rocks, and they bring them home. And when we analyze those moon rocks in the lab, we see that the composition of the soil basically on the moon is identical to the composition of the soil here on the Earth. And that's both a good thing and a bad thing for this theory. It's a good thing because it suggests maybe the Earth and the Moon had common origin. This wasn't like the Moon isn't a captured asteroid that happened to drift in from a long way away. But it was bad because you'd imagine that if this impact occurred, when that material shoots off and is going around the Earth, it's material from the Earth and material from this impacting body would mix together. And so it shouldn't look exactly like the Earth does today. But through the 60s, 70s, 80s onwards, we couldn't come up with any distinction between the surface of the Earth and the surface of the Moon. But now we fast forward to today, and we finally have far more sensitive instruments than we had back in the Apollo era. And what these researchers did was they looked at the compositions of oxygen in the surface of the Moon and compared that to the compositions of oxygen in the surface of the Earth. And in particular, they looked at what's called oxygen-17. And this is kind of a special kind of oxygen. We call it an isotope. And normal oxygen we would call oxygen-16. And oxygen-16 means that there's 16 neutrons at the center of every oxygen atom. Oxygen-17 has 17 neutrons. Now, to form this strange version of oxygen, oxygen-17 takes, a different process. And so what happens is you can kind of link various processes in physics and in nature to the ratio of normal oxygen to strange oxygen that they form. And so by carefully measuring the combination of those, we can see, well, did the same process that formed the oxygen in the Earth's crust form the oxygen in the Moon's crust? And in short, the answer seems to be no. They measured just 12 parts per million different of oxygen-17 in the Moon's surface than they did in the Earth. The hypothesis here is that there must have been a different combination of materials in the body that hit the Earth that then mixed up with just ever so slightly tweaked the amount of oxygen-17 that we see in the Moon's surface today. But 12 parts per million is very small. And this is one measurement, from moon rocks taken from just a couple of locations around the Moon. Each of those regions of the Moon has been shown to have very different geology and have very different composition, all within the sort of normal range for the Earth, but moon rocks from one place don't look like moon rocks from another place. And so the fact that we've made this measurement from rocks picked up from just a couple places on the Moon, it's hard to say this is definitive evidence that the body that struck the Earth was the way that we formed the Moon. But this is sort of the first evidence we have that they're not exactly the same. And that's a good piece of evidence in favor of this impact theory.
So it's almost like can you start to kind of tease out the components of the object that struck the Earth? I mean, is there a way to start to get at a sense of how that was different from the Earth itself, and then how that, it's almost like two parents having a baby, right? That you've got sort of, was it Thea and Earth, and they crash together, and then you got the Moon, and it's going to have components. The Moon is going to have components of the Earth and components of the other progenitor Mars-sized object in its component atoms, especially if that was the impact site is what was then thrown up into space.
All right, so to tease this out better, the best thing we could do is get more moon rocks from the surface. And this would actually be a great thing to do for almost all of planetary science, because a lot of people don't know, but when we say Mercury is 4.4 billion years old, or the surface of Mars is 1.8 billion years old in these areas, every single date that we measure in the solar system is based off the age of the moon rock brought back by the Apollo astronauts. And that was, again, from these 6 particular locations, which we were then able to match up to crater count densities in those 6 areas. And that's the only way that we have to measure things, to measure the age of things in the solar system. And so every additional data point that we could get from the surface of the Moon and bring back to the Earth and measure the age of those rocks would improve and enhance our ability to put ages and dates on things in the history of our solar system.
We should totally send a robot to the Moon to pick up more moon rocks, because it's easy to do with robots. Okay, cool. So let's go.
Return is harder, though.
Well, the Moon, the gravity on the Moon is really low.
No, I'm saying we should do it. I'm just saying.
Yeah.
The Russians did it decades ago. We can do it.
Exactly.
We can do it. Yeah.
Those commies can do it, we can do
But
it.
that's not a good reason to send humans back to the moon, is all I'm saying. Like, picking up a bunch of moon rocks, not a great reason to go back to the moon with humans. To see how long a human can exist on the surface of the moon, a great reason to go back to the moon. Okay, so let's move on with the Hubble Ultraviolet Ultra Deep Field. I got a picture. Brian, you were going to talk about this, right?
Yeah. The Hubble Ultra Deep Field is a patch of sky in the constellation of Thorne-X in which it looks, by any normal view, it would look basically completely dark. And what they did is they took the Hubble, pointed it in this direction, and gathered as much light as they could. And if you think about the scale of this, the size of the area of sky, the patch of sky that they observe, is about the size of taking a grain of sand and holding it out at arm's length. So if you take that and that little tiny patch that looks like it has no stars or anything in it, and take a very, very long series of exposures. So you do multiple exposures with the Hubble telescope. And then you can add up all of those together to see what you get. And what they got was known as the Hubble Ultra Deep Field. And this has been out before, but keep going back to it. So as time goes on, when they've got extra time, they'll turn it back to this, and they'll keep gathering more light at different wavelengths. Well, this latest one, they now have gathered enough light in ultraviolet. So earlier ones have been in infrared and visible, and now this new one gives us ultraviolet as well. So now we have a much wider spectrum of this ultra deep field, which is why the new image looks so much more colorful. It looks so much brighter in many ways because it's got more light at multiple frequencies. So this is an astounding picture because if you look at that, there's about 10,000 galaxies in that little area. And so you're talking about hundreds of billions of galaxies in the known universe if we assume that this type of distribution is everywhere. But in the specific sense, getting this ultraviolet allows us to look at the brightest stars in the early universe. And that helps us understand how the first galaxies formed, how stars formed in the earliest periods of the universe that we haven't had before because we couldn't see it as well in the visible and the infrared.
I cannot wait for the James Webb Ultra Deep Field. Won't that be so great when they do something like that?
It's going to be astounding.
Yeah. And wouldn't it be amazing if we could have that level of resolution just across the whole sky? Like it's, if you just could have a billion.
A lot of areas it wouldn't. A lot of areas it would be rather boring because there's things like dust in the way or other stars which would just kind of wash out everything. It's kind of like watching the night sky when the full moon is out. If you have a bright star in your field of view, that's what you're going to see. You're going to see the bright star. That's specifically why they chose this area, because it's one of the darkest dust-free patches that we can find. And so that's why you can see so clearly for so far.
I just offered you 1 trillion Hubble Space Telescopes and you turned me down.
No, I didn't say it wouldn't be good. I'll take the 1 trillion Hubble Space Telescopes. But what I'm saying is not all of them would be this clear.
Right. Very cool.
But there are other dark patches of the sky. This is only one choice. There are other places to look.
All right. You'll accept some of the 1 trillion Hubble Space Telescopes that I'm offering up.
We're greedy. Scientists are greedy. We have to be.
All right. Okay. So I just want to sort of respond to some questions that sort of collected during the broadcast. This one is about the hybrid star. This comes from Nancy Graziano. What percentage of the general stellar population is theorized to be one of these hybrid stars? How many of them are there probably out there?
Almost zero.
Yeah. Almost zero.
It would be a very, very small percentage. When it was originally proposed, it was accounting for a type of variable, and the name eludes me, but I think there was only about 30 or 40 known at the time when it was proposed for these weird variable stars. So these would still be very rare. Most red giant stars will be normal red giant stars, not these objects. And so it would just be a very rare merger.
Okay. So I'm gonna. I can't even. Oh man, I'm so afraid. I'm afraid to do this, to show this. I'm gonna do it. I'm gonna do it. I'm gonna show it. Which is a restoration. They're working. The folks, the good folks, my dear friends at NASASpaceflight.com are working to restore that landing video of SpaceX, and it's pretty amazing how far they've gotten. So I'm gonna share that, and you can watch, and then I will deal with the copyright takedown requests. And I beg my good friends over at NASA Spaceflight to not send me to jail. So, so you can see the waves, and you can see the landing struts come out, and you can see the breakers, and then splash. And then there's the thrust, and then it's all gone. So, right?
And we have puppies.
Yeah.
Puppies.
So we're there. That's it. That's a great. I cannot believe. Like, if you remember how bad that original video was, and the fact that they've cleaned it up to this point. I mean, it clearly looks like if they had been able to send that video out and go like, here's evidence of us landing in the ocean, everyone would have gone, great video. And it's amazing that they went from how horrible it was to this. Is just astounding. So, fantastic. Thanks to O0XYZABCX0 for sending that in. Guido Bieber asks, why do we need to go to Mars quickly? Do we have a deadline? Is the planet being demolished for a hyperspace expressway? What's the hurry? What's the rush? Why go to Mars?
Well, there's really no reason to go now for Mars's sake. The reason to do it is to maintain continuity in people. You know, one generation of engineers and scientists trains the next generation. And if we stop the manned spaceflight program, which, you know, I would advocate as the alternative to going to Mars, is say, hey, let's build those lots of curiosities and send them across the solar system. Then we have this gap where we don't have a lot of people.
Oh.
And so that's really the big thing. And the report that we were talking about earlier even highlights that sort of highlights the Space Launch System launching only once every 4 or 5 years as not being enough to maintain good technical readiness. And if we're talking about putting off going to Mars for much longer than that, then we're really going to have to reinvent a lot of stuff.
Okay, we got a few. So we got Nancy also notes, hooray for Cosmo Academy. Agreed, Nancy. And then also, Jim Meeker says, I just finished Sondy's asteroid class. It was awesome. Do you understand? You can learn about asteroids from Arecibo Observatory astronomer Sondy Springmann. And there's the great one. Nancy Graziano said, I just took a class with Pamela Gay last year. Cosmo Academy classes are the best value out there. Right? You can learn astronomy from Dr. Pamela Gay for a reasonable fee. So, and now, look at this.
Which means we have to get her to commit to teaching another one. If you're listening, Pamela, you need to tell me when you're teaching your class.
So, you know, these are your heroes, and you get to learn from them directly and interface with them. This is what a bargain. So right now, drop whatever you're doing, go to Cosmo Academy, sign up with Dr. Matthew Francis, and learn about black holes. So I don't have to. All right, let's see.
And we have a class on Pluto that I'm going to be putting up on the website over the weekend. So if you want to know about Pluto, you have an opportunity coming up very soon.
All right. Our friend Roshan Bukhari, who can never seem to watch us live, wants to know what minerals will decide the landing site's frequency for the future manned missions to the Moon or Mars. So do you think that minerals will play any part to where we will land humans on the Moon or Mars?
They will if we have a substantial corporate contribution to a future landing, and that's much on Mars. But there are elements found out there on asteroids and on the Moon that are difficult to find or difficult to extract here on the Earth. And in fact, for asteroids, there are companies out there right now looking to survey asteroids for these minerals and put together a plan to mine them. And what exactly those minerals are, I don't really want to say. Of course, the one that's always brought up for the Moon is helium-3, which is a valuable component of fusion if we ever get that off the ground. But there are, precious resources, what we call rare earth metals here on the Earth, that are relatively abundant out in space. And if we could find those, it's possible to do that in a cost-effective way.
Hugo Burnham notes, maybe Kepler 10c is the result of many planetary mergers. I mean, has that been proposed, Matthew?
That I don't know. The paper that I have looked at declines to speculate on specific scenarios. I think we have a lot to learn about planetary formation still. We're making progress. A clearer picture is emerging over time, but there's still some puzzling aspects. And the question is, why would it merge into a big rocky object as opposed to several smaller rocky objects, or kicking one out of the system, or all these other possibilities? Whenever you're talking about something as complex as merging objects and making one out of it, I don't even know how one would begin that.
All I know is my gut says maybe. Okay, so let's wrap things up. Brian Koberlien, where do we find out more, Brian?
You can find me at briankoberlien.com or on Twitter at briankoberlien. And if you want to check out kids science, go to proveyourworld.org. There's a new series of web videos just for kids, including the Cavendish experiment on gravity.
That is great. So you're still going forward with Prove Your World.
Still going forward with it.
Awesome.
Yep. New video every week.
Right on. Dr. Matthew Francis, where do we find out more?
You can find all sorts of stuff at bowlerhatscience.org. I am also your personal space columnist at thedailybeast.com. That's the latest gig I've picked up. And find me at cosmoacademy.org.
Yeah, I understand you're involved in some kind of online astronomy education group.
Yeah, funny how that works.
All right, Morgan, where do we find out more?
Sign up for my black holes class.
Sign up for his black holes class.
You can find me on Twitter at Morgan Rehnberg. You can also find me at cosmicchatter.org. And I'll be taking your questions over at the Google Plus Space community right after this show.
Right on. Again, if you got a million questions and we didn't get through them today, Morgan will join you over in the Google Space community. Just go to Google Plus, click on Communities, click on Space, and you'll see the posting there, and join in the conversation and hit him with all your doozies.
I will summon Brian and Matt so
as necessary. Okay, great. So I've got one little piece of housekeeping before we go, which is the virtual star party. We've been having a lot of trouble with the virtual star party because of weather and people's busy schedules. So we're changing the way the virtual star party works, sort of on two ways. One is that we're going to be shifting it to once a month. We're going to aim for a quarter moon, around the quarter moon every month. So we'll still get some moon, but it's not going to overpower the rest of the observations that we're looking to do. And we're also going to try and make it at a very set time. So up until now, we've been going later on, like 10 o'clock Pacific, and then that's like 1 in the morning, and that's been really tough for the East Coast astronomers and reducing it. So we're going to stick with a set time. We're going to go for 7 p.m. Pacific time throughout the entire year. Now, obviously, you're saying to yourself, Fraser, you're a crazy person. In the summertime, there's no stars at 7 p.m., and I agree with you. And so we're going to sort of still get the contributions from the East Coast astronomers, but then the West Coast folks and around the world are going to share the photographs they took and sort of try and keep it a little more, have more content about the kinds of photos. So it's really going to be about sort of observing, about gear, about sort of our experiences as amateur astronomers, and then also have some live observing if we can. But we're going to try and really focus on a format that we can do no matter what, as opposed to waiting for nature and people's weather and their schedules to kind of wrap around. And so we'll try to get some more experts join us, more science. So that's kind of how we're going to be changing the virtual star party. And so Scott and I have been sort of working out all the logistics on this, and we'll get more information over the next little while. So the next virtual star party is going to be in early July, when there's on a Sunday that corresponds with a new-ish moon. So just to sort of keep you posted on that. Cool. Well, once again, I am the publisher of Universe Today. You can find you just click subscribe on this YouTube channel, and we will see all of you on next Friday. Thanks, everyone.